So let's take a look and see how the Kane-Ingold-Prelig priority system works, or the CIP system works. In a nutshell, what we're going to do is we're going to assign priorities to groups attached to each carbon in the double bond. And before we get into how we assign those priorities, I want you to kind of get a picture as to an overall picture as to what we're going to do. So, for example, if I have a double bond and I have substituents coming off of it, I'm comparing the substituents on each carbon one at a time. So, for example, if I have two substituents coming off of the carbon on the right, and I assign priority, which we'll look at in just a little bit about how to do that. And the the substituent on the top gets the high priority, HP, high priority, and the substituent on the bottom gets the low priority, let's say. Right? So this is an arbitrary setting. So now notice I'm assigning priorities based on the substituents on that carbon. So now I go to the carbon on the left, and it has substituents, and I'm going to compare its substituents. And I see that the substituent at the top has the high priority, and the substituent on the bottom has the low priority. So then what I do is I compare the relationship between the two high priority substituents, and I see that in this particular case, the two high priority substituents are on the same side of the plane of that double bond, or the same side, and therefore it gets a Z designation. Notice I'm not using cis anymore. Cis and trans are only used for fairly simple alkenes. Once we go to a scenario where you have, multiple substituents coming off of the carbon-carbon double bond, then you have to use Z. And of course, the other possible scenario is when I'm comparing substituents. Let's say, again, arbitrarily, the upper substituent has the high priority, and now I look on the carbon on the left, and now my high priority is the carbon or the substituent at the bottom, and so now I see that the two high priority substituents are on the opposite side of one another. This gets the letter designation E. So this is how we're going to assign the stereochemistry of the alkene and designate it either E or Z. So how do we prioritize? Well, the first step in prioritization is that the atom of higher atomic number coming off of the carbon-carbon double bond has the higher priority. Now notice I'm not comparing the substituent in its entirety. I'm comparing the atom directly attached to the olefin carbon, or the carbon on the double bond, right? So carbon on the double that is making up the double bond is called an olefin carbon. So here I have, trying to compare a methyl group and a hydrogen. How do I compare them? Well, again, I'm not comparing groups, I'm comparing atoms. So I'm comparing carbon, which is directly attached to the olefin carbon, to hydrogen, which is directly attached to the olefin carbon. And since carbon has a higher atomic number of 6 versus 1, then the methyl group takes the higher priority. Let's look at another example. Here I have a methyl group and an OH coming off of the same carbon, and I'm trying to prioritize them. Well, I compare the carbon, again that's attached, and the oxygen that's directly attached. So notice I'm not comparing a methyl to an OH, I'm comparing carbon to oxygen. Oxygen has a higher atomic number of 8, and therefore it takes the higher priority. In these scenarios, it's fairly easy to see, which substituent is going to get the higher priority. But sometimes it's not as cut and dry as that. And so another step is, well, what happens if you have isotopes? Well, for isotopes, that have the same atomic number, you have to then go by atomic mass. So atomic mass breaks the tie. Basically, the isotope that has the higher atomic mass now takes precedence. And therefore, if I had something like this where I'm comparing hydrogen to deuterium, deuterium is still hydrogen. It's just not protium, right? If you remember, harken back from general chemistry, a hydrogen with one proton and 0 neutrons is called a protium. And then hydrogen with one proton and one neutron is deuterium. So deuterium weighs more than the protium, and therefore it takes the higher priority. Now, there are situations in which the atoms attached to that olefin carbon are the same. And so for step 3, when you have non-isotopic ties, they're broken by looking at the atoms attached to the tied atoms. And you keep going until you find a point of difference between the atoms that you're looking at. So for example, here I have a propyl group coming off of the carbon and an ethyl group coming off of the carbon. The question is, well, how do I assign priorities between these two? Because if you take a look, the two carbon atoms that are attached directly are the same, so there's a tie there. What do? You keep going until there is no tie. So you look at what's attached to each carbon. Each carbon has 2 hydrogens and a carbon. That's a tie. So what do? You move on down to the carbon. And now the carbon on the ethyl group has 3 hydrogens attached to it, and the carbon on that propyl group has 2 hydrogens and a carbon. So now I have a point of difference. I'm comparing carbon to hydrogen, and carbon has a higher atomic number, and so it gets the propyl substituent gets the higher priority. Now, lastly, I want to talk about multiple bonds. So the way that you deal with multiple bonds is that you treat each multiple bond as multiple single bonds. What do I mean by that? Well, let's take a look at this, where I have a tert-butyl substituent coming off of the carbon on the top, and then I have an isopropenyl group coming off at the bottom. And so see, I have that carbon-carbon double bond. How do I deal with that? Well, the best way to think about it is to think again about what each carbon is attached to, and then look for the difference. So I can draw my tert-butyl group showing all of the carbon-carbon bonds, and I can draw my isopropenyl group showing that carbon-carbon bond is really 2 carbon single bonds, in my prioritization. And so when I'm analyzing the atoms attached, I see in both scenarios I have a carbon that has 3 other carbons attached to it, right? So for my tert-butyl group, the carbon attached to the olefin carbon has 3 carbons attached, and those 3 carbons each have 3 hydrogens attached to them. And now my carbon on the isopropenyl group, notice, has again 3 carbons attached to it, right? The methyl group, and then 2 carbons from that double bond. And so there is no difference between the two, and therefore I move on. And what I then move on to is, obviously, if I move to the methyl group, it has 3 hydrogens, just like all 3 carbons on the tert-butyl group. But if I move to the olefin carbon, the CH2 group, it has only 2 hydrogens and another carbon bond. And therefore, that carbon bond distinguishes it, and that whole isopropenyl group takes the higher priority. All right, so let's look at some examples and see in their entirety how you determine whether or not they are E or Z. We've determined how to prioritize groups, and now we have to look at how we actually designate them a particular stereoisomer E or Z. So here I have an alkene. Now I'm not going to worry about naming this alkene. I just want to know how to designate it E or Z. What do I do first? Well, first I look at the substituents coming off of the carbon on the left. I have a hydrogen and I have a methyl group. And so I'm comparing the hydrogen to the carbon. I'm simply using step 1. This is pretty easy. And I see that the methyl group takes the higher priority. Now, if I look at the two substituents on my olefin carbon on the right, I have to use some more steps, right? Because if I look, I see there are two carbons that are attached. So those two carbons are the same, and therefore I have to continue on. And I compare what is attached to each carbon. So the carbon on the top has two hydrogens, and it has a carbon. And so the carbon on the bottom has two hydrogens as well. No point of difference there, but it has a chlorine. So the chlorine has a higher atomic number than carbon, and therefore it takes the higher priority on this particular side. So now I'm comparing where the two high priority substituents are relative to one another across that double bond, and I see that they're on the same side, and therefore this would get a letter designation of Z. Let's look at another example. Here I have fluorine and hydrogen coming off of one carbon, and I have a methyl and OH coming off of another. So I compare fluorine to hydrogen. Notice I'm not comparing fluorine to oxygen. I'm comparing fluorine to hydrogen. Fluorine has a higher atomic number, and it gets precedence. On the right-hand side, I'm comparing the OH group to the methyl group. So I'm comparing carbon to oxygen. Again, oxygen takes precedence, and therefore it has the higher priority. Now I'm comparing the two high priority groups, and I see that they are on opposite sides of one another, and therefore we get the letter designation of E. Alright, so let's look at a complete bond line formula and determine stereochemistry. So here you see I'm using all bond line formulas. I'm not using, where I easily see the plane of the board. Sometimes you have to really think about where that plane is. So here I have a situation where the carbon on my left-hand side, how do I prioritize the substituents coming off? Well, notice the substituent at the top it's a carbon, and the substituent on the bottom is a carbon. Well, I go to the first point of difference. That carbon has one hydrogen and two carbons attached to it, whereas this carbon has two hydrogens and one carbon. And therefore I'm comparing that my first point of difference is the hydrogen versus a carbon. Carbon basically takes precedence, and therefore the substituent on the top there is my high priority. Now, I'm then comparing deuterium and hydrogen. I see that deuterium has a higher atomic mass, and therefore deuterium takes the higher priority. My plane of symmetry then runs like this, and I see that both the high priority substituents are on the same side, and therefore this would get the letter designation Z. Alright, so let's look at another example. Here again, complete bond line formula. How do I determine the stereoisomerism? So I'm again going to compare chlorine to methyl, right? Because the chlorine and the methyl are on the same carbon. Chlorine has a higher atomic number than carbon, and therefore it takes the higher priority. And now I'm comparing the methylthiol group to an ethyl group, and I see that the carbons are the same, and the carbon on the bottom is attached to a sulfur versus the carbon on the top is attached to a carbon. Sulfur has a higher atomic number than carbon does, and therefore it takes the higher priority. Now, again, if I draw my plane through that double bond, I see that the high priority substituents are on opposite sides, and therefore they get the letter designation of E. And that's how you assign priorities based on the Kane-Ingold-Prelig rules.